In this video I will look at the sideband noise of low noise oscillators. This one, which is my own design, with 20 HC49 crystals in parallel as the selective part, and this ultra low noise professional oscillator from Wenzel. Both operate on 10 MHz. I'm using a direct conversion receiver, which you can see here. There are also some other things on this table, but the receiver is essentially 4 Schottky diode mixers fed with signals in quadrature to make I and Q. So I have 4 audio signals amplified here and then routed into this box, which is an UADC4 that moves the information into the PC computer. The 2 receivers are fed by the same signal through a hybrid that splits the signal into 2 parts that are equal, and then there are 2 attenuators at the input of each receiver, 6 decibels of attenuation. I first set a modest frequency resolution, about 4 Hz, and I ask for a Gaussian window, and the version 6 here for the first forward FFT means double precision, and I'm allowed to go above 64,000 bins for the transform. This is 262,144 points in the Fourier transform. And of course I have enabled the correlation spectrum because I want to look at the correlation spectrum in order to see noise that is below the noise of each of the receivers. That's why I have 2 receivers. And reduce the sampling rate by 2 to power 8 to get far less speed in the baseband, and a Gaussian window in the baseband also. And I start to collect data. And here comes the carrier, and I click on it, and things are pretty slow. The bandwidth is not very large. I get the carrier at the center, and I move the BFO for it to show 0 here. That's so I can tune for a 20 Hz offset fairly accurately. The level of the carrier, I can read here, is on the average 0. It's the 2 upper, which is the power within the selected bandwidth. And then I move the frequency by 20 Hz. That's as much as the separation from here to here. So it means I should click something like on this spot, and then I see it was an error of 1.1 Hz. I can turn the mouse wheel. Oh. And it's fairly slow, but I'm approaching 20 Hz offset here. And then I have to wait to see the noise floor. I get all sorts of noise when doing the tuning, because then I get discontinuous transforms. The yellow and the green trace are the correlation spectra. The white is the average power spectrum. The yellow is the average of 200 spectra, which is the number up here. That's also the number of average power spectra, the white trace here. The green is the average of the number of spectra I have totally collected, which is now 500. The distance from the white to the green is 9 dB, and the maximum theoretical distance that I could expect is 14 dB, 13.7. I want this to be 6 decibels larger than the measured to have a good confidence in the accuracy of the level I have. So from 13.9 to 8.7, it's almost 6 dB now. So I read the level of the white. This is the average power extracted from the bandwidth here. That's the two upper. And then the yellow number is in dBc per hertz, and it's properly computed the average of the two from the two channels. Because they are not exactly the same and I cannot take the linear average in dB, it's necessary to convert to power and then to take the average of the powers and then go back to decibels again. So what I observe is that the noise floor is minus 133.8 dBc per hertz, and that is the white trace here. And the green is 8.7 dB below that. To reduce the statistical uncertainty, I have increased the number of averages to 1000. So the white trace is a little bit smoother now, and the green also, because I have waited for a little bit more than 1000 transforms. Now I see 8.3, and the average power is minus 133.9. What I have shown is this setup: the oscillator, 17 dB of attenuation, and then the analyzer, the two IQ receivers. And I have calibrated the carrier to show 0. Now I have added an amplitude limiter. It is crossed 1N4148 diodes to limit the amplitude to produce a square wave. First 6 dB of attenuation, and after the amplitude limiter 4 decibels of attenuation, and then the analyzer. And I look at the carrier and see the carrier level here. It's minus 0.17 dB on the average. So I click 20 Hertz away. That's about here. Now I have to wait a bit longer to have a good enough result, because the correlation advantage has improved to something like 11 dB, and it's only 4 dB from the theoretical, so I had to wait about twice as long. Now, with over 3000 averages, statistics is good enough. I have correlation advantage 10.7, and the average power, oops, and I have to wait to be able to read this because there is a bug in Linrad. I have it from this short range, minus 134.1, but I have to wait a little bit more. Well, correlation advantage varies a little bit, 10.3, and the average power is minus 134.3. I repeat because sometimes, like here, there are single events. I think things happening in the crystals, and it could be the crystal oscillator or my receiver, which uses similar oscillators. So I have again set an offset of 20 Hertz after making sure that the BFO was on the correct frequency, and also checking the carrier level here, which was now minus 0.2 dB. It has drifted 0.03 dB over this time interval. So I have to wait again. When the number of spectra is not enough, this value is unstable, and it can be too good and it can be too bad. So I have to wait for the statistics to be good enough. The average power spectrum is correct all the time because I didn't clear it or so. Now the advantage tells me 12 dB almost, but when looking at the graph I can see that the curve here is noisy, goes up and down, and at this time it seems to be a minimum here. The smooth curve is maybe 1 dB higher than what I'm reading at this moment. So again, just wait. Now with about 4000 averages I read 10.15, well 10.10. It goes up and down a little bit. The curve here is fairly smooth now, which means that value is reasonably accurate. And I evaluate the power spectrum, and again there is a problem with this bug in Linrod. Well, 134.4 and 10.2. So I skip this value with only 200 averages and take the one with 1000, which gave me minus 142.2, and now I observe minus 144.4. That is a 2.2 dB improvement. 2.2 decibels is 1.66 times. So if I set phase noise to 1 in power units, the amplitude noise is 0.66 of that. So the amplitude noise is 1.8 dB below 144.4, and that's minus 146.2 dBc per Hertz. So AM noise is absolutely not insignificant. It does contribute, and it's fairly easy to remove it. I have now connected the Wenzel LO, and the carrier is 0.8 decibels below the calibration I made. And I am on the carrier, and I set this BFO for the indicator to show 10.0, and I step away 20 Hertz. Then 20, that's about here. Like this, and then I wait again. The Wenzel oscillator gives me 12.1 dB correlation advantage, and the average power is minus 134.9. Now I'm running the Wenzel with an amplitude limiter, the same limiter as before. And now the carrier is minus 24 dB or so. The Wenzel oscillator has been running with the amplitude limiter for quite some time now. 17,000 averages, and the correlation advantage is 16.5 dB. That's quite a lot. And the average power, hopefully, is minus 134.8. With the Wenzel oscillator, the AM noise is significant. Removing it brings the total noise down from 146 to minus 151 dBc per hertz. The difference is 4.7 dB, that's 2.96 times. So if I set phase noise to 1, the amplitude noise has to be 1.96, 2.96 minus 1. So that's 2.9 dB above those 148, above those 151.1. That makes minus 148.2. So these are my final results for phase noise and amplitude noise for the Wenzel. Then I look at this sheet, which is a measurement made by a FSWP from Roden Schwarz. It is a measurement of phase noise as well as AM noise. The blue trace is AM and the black trace is phase noise. And I can read minus 138 and minus 148. So on AM it is very noisy, much noisier than what I have found. I found minus 146. While phase noise 148, well, I find 3 dB better. And I find it very difficult to believe that there is something wrong with the way I am measuring these things. I think it is pretty obvious and accurate. And it's not a black box with hidden insides. So here are the 4 measurements. You already have seen this with my homemade oscillator, the attenuator or attenuator, limiter, attenuator. With the Wenzel, 1 dB attenuation and then the analyzer. And for the limiter, the Wenzel, 6 dB gain and 6 more dB of gain, and then 4 dB attenuation to have the same level into the amplitude limiter, and also to protect this amplifier from the impedance of the limiter. And then a 4 dB attenuator, as before, and into the analyzer. And of course I expect the same carrier level here, analyzer with 4 dB attenuation in front of it from the limiter, as I had here. And it's the same within accuracy. And here is the schematics of the amplitude limiter.